All right, so this is hopefully the final segment of atoms and elements. And so we've already discussed this a little bit. We talked about the S block. So here is our S block. It's the first two columns of the periodic table. So we have group 1A and group 2A. Now again, we want to include helium over here because helium does complete the first period. And so it is actually an S2 element. So for your ideas here, we talked about alkali metals. All your alkali metals will end in S1. All of your alkaline earth metals are going to end in S2. Now again, as I pointed out, you have to include helium here, but it fits better later simply because of the properties of the noble gas. Now if I'm moving directly across the periodic table, the next block we run into is the D block. And I'm going to tell you a little lie here just to make life a little easier for us at this level. And so here we see we have a D1, D2, all the way across to D10 with no breaks. And that's not quite true. Remember, we're measuring actual energy levels. And so we have a half shell kind of thing going on here. And so I'm kind of lying to you about chromium and copper. What chromium and copper will do is they will steal an electron from the S block and put it into their shell to give a half D here and a full D over there. Now we're not going to worry about that. So I just want to point this out because if you go online and you're on Google and you type in electron configuration for chromium, it's not going to look like what I'm expecting you to give me as the answer. So I'm expecting you to tell me that it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, that's what I'm expecting for chromium and 3d9 for copper. Now typically I don't put these on exams because I don't want you to get confused with those two. I'll just pick a different element along the transition metal, and that way it will follow the pattern that we're expecting. All right, so after the D block, we hit the P block. Now remember, helium would be sitting right here, but we already moved it over because it's S2. And so here we see the P block is P1 through P6. And then last but not least, down at the bottom of our periodic table, we'll have that F block. And I'm telling you lies here again. Again, the half-filled shell. It turns out there's also other different formats that can happen here. And it's a lot of information that we don't need to worry about in basic and general chemistry. And so here it'll just be F1 through F14. Okay, and that's your inner transition elements. Now, what we're going to be using these blocks for again is electron configurations. And so I started explaining these using oxygen, aluminum, and selenium. And so now what we're going to do is we're going to do phosphorus together. And again, what you're going to do is use your periodic table to do that. So if we're looking at phosphorus, we're going to have 15 electrons. Now, how do I know 15 electrons? Well, remember, I'm going to get that from the atomic number, and we're going to be doing electron configurations of neutral atoms. So protons have to equal electrons. So I'm looking for 15 electrons. Now, if I want to go straight to the electron configuration, I can just follow along with my periodic table, starting with element 1, helium. And now I have to go through the first period. So I need hydrogen and helium. Excuse me, I said hydrogen. I said helium, but I meant hydrogen. Hydrogen and helium will be the first period, and that's going to be 1s2. Then I'm going to skip down to the second period. For the second period, I have to go through lithium and beryllium in order to get to phosphorus. Well, that's going to be the second energy level. That's the S block, and we're going to have 2. Then we're going to skip across to boron. Boron through neon will be 2. That's the P block, and we're going to go through all 6. And then I'm going to skip to the third energy level, the third period. We're going to have 3 S2, and then we're going to go to aluminum, which is going to be the 3P. However, this time I'm not going through the entire P because I need to get to phosphorus, and phosphorus is the third one in, so that's going to be 3P3. Now again, some tricks of the trade. What we can do is sum these up. We have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. And so all of these superscripts up here should sum up to give us 15. All right, and that's how we can do our electron configurations using our periodic table. So all you have to do is look at the element, figure out how many electrons you have, then follow your periodic table to put all those pieces together. All right, hopefully that's making sense. If you need some more help with this, get a hold of me. If you want more practice, let me know. I'll try to put some forms up in the inside the folder on D2L so that you have some extra practice with some answers. All right. So again, we want to finish this chapter out looking at different patterns on the periodic table. So the first pattern we see are the electron arrangements. Now, since one part of the atom sees as the other parts of the atoms are only the clouds, then the electrons become the most important part. Okay, so it's more importantly that we're only looking at the outside orbitals, and those orbitals fill up in a regular pattern. And that's what we were just looking at. The other thing that's going to happen is, since those things are doing that, they're doing it by pattern, the other thing that's going to happen is the reactivities are going to have the same patterns. Atomic size is going to have the same pattern, right? And so that's what we're going to look at next. We're going to look at size, and then we're going to look at ionization energy, which is basically reactivity. So trends in atomic size will be influenced by two factors. First will be the energy level. You can think of it as like an onion. The more times I put a layer on, the bigger the onion's going to get, right? So the more energy levels, the further away the outside electrons are going to be from the nucleus. The higher energy level is further away. The charge in the nucleus is growing. So as I make that atom get larger and larger, I'm also adding protons to the center. Remember, it's got to remain neutral. Okay? The more charge will pull the electrons in closer. So the two things that are going to influence atomic size then are energy level and charge on nucleus. Energy levels means we're going to be adding, making the layers bigger. Charge on nucleus means as I put protons in, I'm going to be pulling the layers in closer and closer and closer. Okay? So group trends. As we go down a group, each atom has another energy level. So it's pretty obvious what we think is going to happen here, right? It's going to get larger as I go down a group. So hydrogen should be smaller than rubidium as I move down. Now periodic trends are where we're going to get thrown off a little bit. So for periodic trends, as we go across, the radius is actually getting smaller. Now here's where that charge on the nucleus starts to impact. Because the charge on the nucleus is going up, it's pulling that layer in each time we add a proton. And so as it's being pulled in, it's getting closer and closer and closer. So even though I'm adding more electrons, I'm adding more protons at the same time. The more charge I have, then the outermost electrons are going to be pulled in closer, which means moving from left to right, we're going to see that the atom actually gets smaller. Now, if I were to graph this, it's going to look kind of wild, something like that. So here's hydrogen. If we can get this to show up, there it goes. Here's hydrogen. All of a sudden we add an energy level. As we move across the energy level, it gets smaller. Add another energy level, goes across, it gets smaller. Add another energy level, starts to get smaller. We get a little bump here. That's when we add that D block. All right, so we started getting those D elements filled up, and then it smalls out again. Add another energy level, and then we see that block again for those D elements. All right, ionization energy. Well, what an ionization energy is the amount of energy required to completely remove an electron from a gaseous atom. So I'm going to take the atoms, I'm going to get them into the gaseous state, and I'm going to go in and I'm going to pull an electron out. Okay, that's all we're going to do. So when we remove that electron, it's going to make a +1 ion. Now, what you might not realize yet is that some elements would love to get rid of their electron. So we haven't really talked about the octet rule yet. That's coming. That's the next segments, actually. So when we make a +1 ion, we move that electron out. Some of the elements actually want that to happen. And so it doesn't cost me any energy at all. They almost like want to hand me the electron. Yes, please take this. Other elements don't want to lose an electron. So it's going to cost me a lot of energy to try to pull that electron out of there. So they don't want to give that electron up. Now, when we do that for the first electron, we call that the first ionization energy. So obviously we can do that for more and more electrons. We'll get the second ionization energy and the third ionization energy. Don't really care about any of those. We're going to be looking at basic trends. So we're only going to be focusing on the first ionization energy. Okay, so again, the second ionization energy is always going to cost me more than the first. But again, all I really want to focus on is the first ionization energy. So for your group trends, as you go down a group, the first ionization energy is going to decrease. Well, why is that? Well, remember when we went down the group, what happened to size? The atoms got bigger and bigger and bigger. It's going to be easier to pull an electron out if it's further away from the nucleus. So the further away the electron is, the easier it is to grab. Okay? The electron is further away. There's this thing called shielding. So as I add layers, Like, so layer 1, energy level 1 is going to shield energy layer 2. If I fill 2, now 1 and 2 are going to work together to protect and shield for 3. And then if I add 3 to 4, so forth and so on. So I'm adding more and more shields. Those same layers that are making it go further away are going to be acted as shields from the nuclear charge. So periodic trends, just the opposite. Remember, the nuclear charge was getting stronger and stronger. The atom was getting smaller and smaller and smaller. Well, now it's going to be harder to pull the electron off. You have the same shielding, but we have that increase of the nuclear charge. So the ionization energy then is generally going to increase from left to right. Now remember, these are just generalizations. I'm not going to give you numbers. I'm not going to expect you to like compare numbers. I'm just going to ask you, based on their location on the periodic table, what do you expect to see? Okay, so if I'm looking at an ionization numbers graph, a little harder to make sense here, but what you see is there are your periods, period 1, period 2, period 3, period 4. Okay, and so you can see it's getting a little easier to pull them towards the bottom here, down in here, way harder to pull up in there when we have full energy levels. Now, what is it I'm going to ask you to do? Again, it's going to be generalizations. So as the atomic size goes across from left to right, it's going to decrease. Now, the ionization energy is going to go up. So they're opposite of each other. So while I'm asking you to know 4 trends, technically it's only 2, because if you know 1, then the other one is the opposite. So if the atomic size goes up, then the ionization has to go down. If the atomic size goes down, then the ionization has to go up. And we see that when we're looking at the group trends. Atomic size will increase as you go down the group, but the ionization energy will decrease. So as the atom gets larger, it gets easier to pull an electron out. All right, sample questions. Circle the larger element in each of the following: carbon or lithium. So what I'm going to ask you to do is come onto the periodic table, find carbon. So carbon is going to be right here. All right. Find lithium. Lithium is back over here. So what should happen here? Well, atomic size decreases. So we would expect lithium to actually be larger than carbon. And so there we go. We were right. Lithium is larger than carbon. All right, so grab a periodic table and we'll go through the rest of these. We have gallium versus boron. So boron is number 5, and gallium is just 2 below it. So it goes boron, so I'm going down the group: boron, aluminum, gallium. Boron is at the top, so it should be smaller than gallium. So we're expecting gallium to be larger. And again, we are correct. All right, chlorine versus aluminum. So chlorine is going to be number 17. It's in group 7A. And aluminum is number 13, and it's in 3A, and they're in the same period. As I go from left to right, the elements get smaller. So aluminum should be larger than chlorine. All right, hopefully we're getting the hang of that. All right, the next one. Circle the element that has the smallest ionization energy: nitrogen or phosphorus. So nitrogen is in 5A, it's number 7. Phosphorus is right below it, also in 5A. So which one should have the smaller ionization energy? Well, smaller ionization energy means larger atom. So which one is the larger atom, nitrogen or phosphorus? And of course, if we're going down the group, phosphorus should be larger than nitrogen. All right, how about iodine, I, which is in group 7A, versus fluorine, also in 7A? Well, we're looking for the smallest ionization energy, which means we're looking for the largest atom. And so iodine should be much larger than fluorine. And so once again, we're correct. Now last we have sodium versus cesium. So sodium is in 1A, it's in period 3. And cesium is also in 1A, but it's in period 6. So as I go down the group, we know cesium should get larger and therefore have a smaller ionization energy. All right, notice that all of our comparisons on here were either going to be in the period or the group. None of them were diagonal, and that's what you should expect when I'm asking these style of questions. All right, if you go diagonal, then you have the two things competing against each other or adding together. I'm not expecting you to understand those things. I'm not asking you to look at numbers and compare numbers. I'm asking you to look at trends in the periods and in the groups. So across and then up and down. And of course, as long as you remember which one's getting larger, that leads you to the ionization energy as well. All right, that concludes atoms and elements. We have finished this chapter. Hopefully you're having a good week. And so if you have questions, so far so good, everything looks like it's going well, then that's great. If not, and the road's starting to get bumpy, make sure you come get some help right away, whether it's from me or one of the tutors in the tutoring center, or maybe some other avenue of help. Again, you can shoot me an email. I can see what's going on for you and see if I can find you something if you're not able to meet with me. All right. Have a great day. Talk to you soon.